Hi class, it's Bill Berry here. We are working through our tree data structure lectures, and we had one video that set up some of the terminology and gave you the basics of what are trees, what are binary trees, binary search trees. So hopefully we got all that clear. We talked about traversing the trees. So all of that is great. That set us up for success. But before we move into tree algorithms and looking at the cool recursion that we're going to use there, we need to stop and talk about one particular topic that is a little bit sticky for some reason. With all of the Java knowledge that you have and programming that you've taken, this one particular thing may not be as clear as it should be. So we need to clear this up before we move into the algorithms for trees. Otherwise, our code's going to be overly complex, right? We're going to think about it in a harder way than necessary. So let us jump back down and look at this idea of x equals change x. This is an algorithmic pattern. It's not a design pattern, just an algorithmic pattern of something that we're going to need to use. So let's look at why. So I'm going to show you some code. I'm going to let you pause the video a minute and you tell me what this is going to print. So pause now and see specifically, is this line going to print something different than this line? So pause now. So our brains may have told us that we have swapped this data and that these now are going to be reversed, that A and B are going to show the reverse of their values, but they don't, right? Why did that happen? Well, this looks like it tried to swap X and Y, but it did not end up swapping the A and B from up here, right? A and B are still unchanged. So the swapping down here, while it may have looked like it was going to do the work, did not actually do the work at all, right? Now, why doesn't that work? Why can't you swap that? Well, we're going to get to that and some examples of it in a minute, but one thing that you might say as well, of course, those are primitives. So when you work with arguments that are primitives, of course, it's just copying the values, right? So it doesn't actually know where A and B live in memory. So of course, it's just going to copy the values down there. So of course, swapping the values down here isn't going to change anything. Well, okay, so you would be right in that regard. So that is a good call, right? But now let's move forward and see if another example with object references, we'll use strings, but it could be something else, right? Actually, we're going to use students, right? So that we don't think that it's only strings or anything like that. So let me show you this other code and then you decide if it's going to be swapped. Okay, so here's the same example, but now using student references. So these are clearly object references. So now I want you to again pause the video and tell me whether student A and student B have swapped places. So pause and think about that a minute and then resume. So interestingly here, many Java students at this level will believe that these two things have swapped. They will convince themselves that because the references here are not primitives, but instead they are references, they will believe that this swaps the two students. But the truth is, no dice. It has not swapped these two students up here, right? It did some swapping work down here. It did not swap any students up here. So, okay, now what? If you're super clear on how references work and how Java passes data around, maybe you see that this isn't going to work, but I bet most of you will believe that it did swap the students. It doesn't. So let's now go back and explore this and talk more specifically and give you examples of why this doesn't work and in fact can't work in Java. So let's go talk about first how parameters and arguments work with primitives. Now generally people will use these two terms interchangeably. Beginners will use the terms interchangeably. No, let's talk specifically about the fact that it's an argument on this side and a parameter on this side. So we have up here a call to function foo and it passes in y, and over here we receive a parameter, right? Think of it as a local variable, right, called x. So how exactly does Java work with this? So let's put that into motion. When you make this call, what happens? Well, it's going to copy that value, right? So this number in this box was a 5, so it copied the 5 down here to this other box. Now up here we call it y, down here we call it x. This is, remember, think of parameters as a local variable, so this x is not the same as y. It's not pointing to the same place in memory. It's a different place. It's a local variable called x. It just happens to have the copy of the contents, so now this has a 5 in it. But now what do we do here? We add 5, so now the value has turned to 10. Well, great. X now has a value of 10. That doesn't have anything to do with y. Make sense? So that's kind of clear. Maybe with primitives, we're very clear on this, right? So maybe our brain was already working correctly, but just wanted to make sure because I'm going to show you the same thing happening with the references and see if you can follow that. Now, just for those watching, those who have availability of the slides, when you look at this slide, it's not going to make any sense because there's builds on it and it's going to be funny. So just realize this is a video slide, not a static slide that's going to work for your brain. Okay, so now let's do the same thing though with an array, right? Array will be working with a reference. We could use student or whatever we want. So again, we're going to have a function called foo. We're going to pass it something. That thing we're going to pass it is going to be a reference to an integer array, and it's going to be called x. So let's do the setup here. Remember that with a reference, what's found at y is not the data for y, it's a memory address at which the data is going to live. That's how references work, right? So if you tried to just print one of these things, that's why Java is going to print something that looks like this, and it says, hey, this is an address, this is a memory address, right? This is not the data you're looking for, it's the place where the data lives. If we then go to that memory address, then we would see the array, and then of course the data of the 0th element being 3, as we said here, would be there, right? So this is a reference. It points to the place in memory where the data lives. That's how references work, right? So far so good, right? Okay, now what happens when you pass that reference to y down to here? Well, remember what we did in the previous slide with primitives? We copied whatever's in the box here to here. Guess what we do in this case? We copy the thing that's in the box here to here, right? So the way that that worked did not differ between a primitive and a reference. The only difference is the thing in the box happens to be an address, not a value, right? Not a plain primitive value. So at this moment, y and x do in fact point to the same box, same place in memory, same memory location where the same array lives. So far so good. Now, think about it. If we were to change the contents right now, right, if we were to only change the contents of, let's say, the 0th element to a 4, this would change both of our copies, right? So the interesting thing with a reference is you can change the target data. You can follow the reference. You can dereference it, and you can change the data there. But that's not the same thing that we're trying to do here, right? We're trying to actually point it to a new array, like we were with the new student when we did swapping. So what happens now? Let's continue the code here. This is what happens right here, right, when we're ready to start. What happens here when we allocate a new array that is, again, the same size? Well, okay, so let's say this location in memory, we create this new array, and we have 0, and of course Java has initialized the thing to 0. Great. Now what happens when we say x equals, remember, when we say equals with a reference, we mean points to the same thing as. So what happens now when we say x equals that thing? Now x is pointing to this thing. Make sense? Now if we change the 0th element to 5, sure, we are changing the 0th element of this thing to 5. What does that mean over here? It means absolutely nothing now. Because now x, our local variable, is pointing to something different in memory because we have repointed it right here. We created something new, we repointed it at something new, but we are repointing our local variable to that. So now we can change this all we want, but that is not going to change this. Do you see what we're getting at here? You can change the thing being pointed at, but you cannot change the pointer used to point to that in the calling program. There is nothing that you can do that will change this in the caller. You can change this for your local value, as we've done here, your local copy, but there is nothing that you can do that will remap this pointer because you don't have where this lives in memory. Does everybody see that? You have this, which is where this lives in memory, but you actually don't know where y lives in memory. So you cannot change the value of y. You can change what y points to, but that's a different problem here. That's our swapping problems. Everybody see that at this point. Okay, so again, this is not a slide that you're gonna read. When it's a static slide, this isn't going to make no sense. So how can we internalize all this? What can we say about this? First of all, we got to be clear. Java passes by copy. Right? So there are languages where you talk about passing by reference. I hope we have never used those terms when we were explaining Java to you. I hope nobody ever said to you passes by reference. Java does not pass by reference. Java always passes a copy, right? So it turns out that when you pass a reference, it's going to just copy, but it's copying a different thing, right? It's copying an address, but that's not the same thing, right? It always makes a copy of whatever's in the box and puts it down there in the parameter. So if you pass a reference, you get a copy of the reference. That's stored in your local copy. You can alter the target object, right? So if you pass a reference to an array, you can go change that array, sure. Or if you pass an object, you can call that object set methods to alter that object. Sure, absolutely. But what you can't do is change the reference itself from the caller. If the local copy of it gets reassigned, that's the local copy, has nothing to do with the caller. So again, the thing that we want to see here is a function, a method, can do nothing that affects the caller's reference, only the caller's referenced data. Hopefully that makes sense to you. You might have to watch this back a couple of times. This is a little bit of an eye-opener for a lot of students of Java at this moment, right? You thought you maybe had this magic with references, but no, you don't. Now there are languages where you can do that magic. For instance, in C, you can say, hey, the thing that I'm getting here is an address. Right? This is going to be an address of where an integer lives in memory. Right? This is an address of where an integer lives in memory. You can write this swap function now, right? Because you have to be passed an address, and therefore you can remap those addresses because you actually know where the address of x is, right? Not what x points at. In Pascal, there was a special declaration modifier, a parameter modifier called var, and var says, yeah, you can actually know where that thing is in memory, so you can receive it that way. But Java is not in this list, right? Java's not here. So hopefully that all makes sense now. Let us now go look at the algorithmic pattern and why we need to do this. So this will happen. You will write this code not understanding the things and even understanding what we talked about. Sometimes you will write this code and it will befuddle you for a little while. You have this method called transform where a point is passed in and then you try to create a new point and take the data from the old point and fix it all up and then reassign it. Right? Do you see that that does the same problem, has the same problem as before? You can't do this, right? When you do this, you're pointing to a new local copy. You are not changing the caller's version. So this has that problem. And when you try to call this with this transform, you are not going to affect P as in terms of pointing to something new. Now, if this instead changed the data that was pointed to in this point object, sure, that would be fine. But reassigning it, pointing it to something new, this is the problem, right? This doesn't work. So how do we fix it? Well, strings give us a clue, right? With the string, partly because of immutability, right? That's why you think about it with a string. But when you call certain string functions, you know you're going to restore it, right? You're going to store the value because you know that this is going to point to something new, right? It's going to point to an uppercase version, but strings are immutable, so it had to create a new version in memory, and now you're going to point to it. So you know that you have to store this again, right? Or else this is just thrown away. So if you want to retain the uppercase version, you got to restore it. Well, with point, we do the same thing. Instead of having a void instead of an actual data type, why don't we return a point? You pass me a point, I create a new point and fix up the old point's data, but instead of just trying to think that point is going to be changed in terms of a reference, which we know it can't, I'm just going to return the new point, right? And then that return's going to be there, and on the other side, on the calling side, you're not just going to call transform P, you're going to say P equals transform P, because you know that the caller may have pointed you to something new. So every time you need to do something that might have changed it. Now, maybe this didn't need to actually make a new point, right? Maybe it did its work without doing that. If so, maybe this still points to the same point it did before. If so, oh well, right? Doesn't hurt anything. But this takes into consideration to the fact that the function that you called, the method that you called, might have pointed you to something new, and therefore we have to store that again. So do you notice this is now the x equals change x. P equals some method that might have changed what this points to, and P is the parameter, right? P is the parameter here. P is being stored again here in case something new is now being referenced. So maybe in retrospect this seems straightforward, but again, a lot of students do not have this quite right in their brains, do not understand the Java passing mechanism when it comes to trying to do things like this. So it was a necessary thing. Sorry, it's taken a little while longer maybe to get it clear, but it's a super important thing because I promise you will write some of these algorithms and you will stare at them and you'll just say, oh gosh, it just doesn't make any sense. This is a reference. Why is this not working? Well, yeah, references don't work the way that you thought they did. There's some little mysteries behind there that hopefully now we've cleared it up and cleared up passing by copy, which is what Java does. So hopefully now, as we talk about the tree algorithms, they're going to make a lot more sense to your brain, right? And as I said, they're going to make the algorithms a lot easier. They're going to make the algorithms more straightforward, but they're also going to look a little strange unless you understand this x equals change x concept. So hopefully that cleared up some things and made your Java a little sharper. So thanks for watching this video. And now we will return in the next video to our regularly scheduled program which is how can we write algorithms that manipulate trees. Fun stuff coming. So continue watching that video. Thanks for watching this one.